Hello students, welcome to our next lecture on random networks where we will discuss one of the most fascinating part or theories of real world networks which we call as the small world property. So when we talk about small world phenomena, you might have heard this expression called as 6 degrees of freedom, which means that on an average, you know everybody on this earth by at most 6 people or acquaintances between them. For individuals who live in the same town or on same campus or same city, this makes sense that yes, it's not a surprising property. However, if I say that even if you have never been to California or to Japan, you would still know somebody there by at most 6 distances between them, and that's what we call as a small world property. And in this discussion we will give to make it more concrete mathematical aspect and try to understand what it would mean in the context of networks. So here I have drawn my own network. This is a very small network that, let us say that there are some students who are in this class, and I know I know Anshuman very well, I know Harsh very well, and I know Aishwarya very well as I teach them. And that means that if I am here, I know all of them. And Aishwarya, if she doesn't know Anshuman by a direct edge, she would know Anshuman by two by just crossing one acquaintance, which is me in this case, and hence Aishwarya and Anshuman are just 2 degrees apart. Now, if I say that in similar fashion, I know somebody who knows President Obama named Stephen Flynn because I wrote a textbook with him, and Stephen Flynn was the one of the advisors of President Obama on his resilience team. That would mean that I also know President Obama by 2 network distance. And what it would mean for Harsh, Anshuman and Aishwarya, that they also know President Obama by 3 network distance. I've tried to make this example as realistic as possible because I have never met President Obama in person, but that still means that we are part of this small world where I can reach out to him because this guy knows him, and if I have to send some message, I will request him that can you, when you meet him next time, can you tell him this, or something like that. So the point that I'm trying to make is that in network science you can transmit messages, and this is of course is based on assumption that Steve Flynn and President Obama, they are talking to each other on continuous basis. Or we can construct these edges. If they have talked at least once, we will say that there is an edge, and in that case the efficacy of transmitting message may not be as realistic as I am portraying in this example. However, if Harsh has to say something to Anshuman, he can just say it to me if they are not on good terms, and I can transmit that message along. So this is what we mean by the small world property in a network. So what it implies in network science, let us try to understand. In network science, when we say that there is a small world property, it implies that distance between a pair of nodes is short. Now the question is what this short even means, and we'll try to answer these two questions, that what this short even means, how short is short. Short could be 5, 6, 600 depending on the network width. And second question that we will try to answer is how we can explain existence of such short distances in giant networks which have size of a few billion nodes. If you talk about social networks, assuming that everybody living on this earth, currently around 7.5 billion people living on this earth are part of this giant social network, how we can expect that we are just 6 degrees away from each other? So that's what we will try to explain, what these short distances are, and we'll make use of some statistics and probability again. So let us begin answering these questions. And to answer this question, we will take some help from the random graph theory or random network theory that we have learned. So what we will do, on an average, we know that you will have k neighbors if you are a part of a random network. That means your neighbors will also have another k. on an average, and this chain will continue. That means if you go n network, if you cross d edges, let us say that this is a network and you have 3 degrees here, your friends have another 3 new degrees, 3 new degrees, and so on, right? So one, you can argue that you should also count this, but but this would become clear that given the summation or the case that we are going to deal with, we are assuming that we are near to connected regime, and k is much average k is much higher than 1. So we can assume that each node has on an average degree of k, and when we go one edge away from this is the root. So if you go one edge away from the root, you can expect to encounter on an average 3 neighbors if the degree of this network is 3. Similarly, you stand here and you go to the next neighbor, on an average you can expect 3 more persons. Similarly, from here you can expect 3 more persons, and in total you can expect 9 persons, because this guy had 3 neighbors, each of this neighbor had 3 more neighbors, and so on. So you can expect that as you are going ahead, number of nodes you can expect at distance d can be written as root itself plus k, which are immediate neighbors, plus k square, which are neighbors of neighbors, plus kd. And this is an assumption that k is much greater than 1. If k is not much greater than 1, this nd should be written as 1 plus on an average k plus k minus 1 times k plus k minus 1 square times k, and so on. However, for random networks, we can go with this assumption. For Kelly tree example, which is also given in your assignment, this assumption would be better, but the approach to solve this problem would be similar. Now, one thing is for sure, that all the networks that we are dealing with, they are finite. That is, number of nodes have some upper bound. For example, if you are talking about social networks, Earth's population is an upper bound. So this ND should never exceed n. So number of nodes you would encounter when you cross all the possible edges in one direction should be approximately equal to n. And if you see that this 1 plus k square up to kd, what it forms? It results in a GP. So we can say that ND can be written as k times d plus 1 minus 1 upon k minus 1. I have just taken a GP summation of this particular equation, and this would happen that the upper mark of this is ND max, which is equivalent to k upon d plus 1 minus 1 upon average k minus 1. When k is much greater than 1, we can ignore this minus 1 from here as well as minus 1 from here, and we can write ND max is proportional to average k raised to power d plus 1 upon average k by ignoring minus 1 terms, which implies ND max is equivalent to average k raised to power d. Taking log on both sides, we can write that log of n, because the number that you are going to encounter is maximum of n. So number of nodes you would encounter by the time you reach end of this particular network would be n, and this is equal to d max because this diameter is at the end, and hence when we take log on both sides, we can write this as ln n upon ln of k, and this is the approximate estimate of d max. So this is a powerful relationship as it represents what we call as small world phenomena. What this small world phenomena means: if the number of nodes increase in a network, the diameter on an average of a given network would increase by the log of number of nodes, and the more denser the network is, higher would be the average degree. For example, if you are near a connected regime, you would know that average degree itself is log n or closer to that, and you would expect that diameter will shrink rapidly. However, when you are in a fragmented regime or k is less than 1, this particular number would become erratic, in a sense that the denominator here would be much higher, or if it is just slightly lesser than 1, you can also expect some negative number, and then you are going to get a measure of some negative distance which may not make much sense, right? So the point here that we are trying to make is that this entire derivation is based on the fact that average k is much greater than 1, and you are away from the critical point that we have discussed before, and this gives rise to a small world property, that is, on an average, as number of nodes increase, the network distance increase as a logarithmic function of that. Now this is a function for d max. When we say that, more refined definition of, because d max could be denominated by some distances which are abnormally large. So in mathematical world, we also define small world property as a network in which average distance is a function of log n upon log of k, and we will use the natural logs in this case. However, when we have to make some point, it's okay to use this, instead of dealing with log to the base e, we can always draw approximations using log to the base 10. So we have to be mindful of that when we solve some examples, when we are trying to draw the some rough analogies between real world system and mathematically convenience that log of 10 has to offer. Now, what does this mean in the context of some systems? Let us try to look into that. Consider a straight line. This is also a network, that is, everybody is connected like that, and we can say that here on an average the d max is proportional to number of nodes, and we call this as a one-dimensional lattice. Similarly, you can also draw a two-dimensional lattice, something like this, where these are the nodes and these are the edges, and here d max is proportional to n raised to power 1 by 2. 1 by 2 for three-dimensional lattice, it would be n to the power 1 by 3. So we see that this is given that this is a polynomial dependencies, and as the n increases, the distance or average distance or maximum distance would increase rapidly, indicating that lattices, the length in lattices like one-dimensional lattice or two-dimensional lattice, lengths are significantly longer than in random networks, where d max we just showed is function of log of n upon log of k, and hence we say that this small world property is a typical signature of ER networks or random networks. To make a point, let me take an example of the social media. Let us say that roughly we are 7 into 10 to the power 9 people on this earth, and if we are connected as a square lattice, that is, all individuals are interacting like this, and there would be around 7 into 10 to the power 9 nodes, you would expect in this case that the average distance would be roughly, if we go by the approximation, is 7 into 10 to the power 9 raised to power 1 by 2, which is approximately 83,000. That is, on an average you are separated by 83,000 individuals between two persons. However, when we look at the random networks, we can say that this average distance should be ln of 7 into 10 to the power 9 upon ln of 10 to the power 3, because we assume that on an average one person knows 1,000 other persons on this earth, and hence average k can be approximated as 10 to the power 3, and you see that this number comes out to be 3.28, which is not as bad or not that far away from this 6 degrees of separation that we started this discussion with. So what it means that on an average, all individuals on earth should be within 3 to 4 distances or handshakes away from each other, and this estimate is indeed closer to from where we started our discussion. Now, second question arises: all real world systems small world? Are all real world systems small world? So the answer to this question is they are not only small world, they are ultra small world. And what this ultra small world means, we will cover this discussion in our next lecture when we compare real world systems to Ardoshreni networks, and this will make more sense. Now let us move to our next topic of discussion, which is the clustering coefficient in the context of Ardoshreni networks. If you remember, we say that if you have a network, let us say A, B, C, D, E, A, B, C, D, and E, and we are interested to determine what is the local clustering coefficient of A. We say that local clustering coefficient of A is defined as actual number of edges that neighbors of A has divided by possible number of edges that their neighbors can have, which is number of neighbors into number of neighbors minus 1 upon 2, and these are the actual number of edges the neighbors have. Now for example, A has two neighbors B and D. There is no direct edge, so LNA reduces to 0, and hence local clustering coefficient of node A is equal to 0. However, if let us say there is a edge between them, now A, B, D, the neighbors of A, B, D, everybody is fully connected. You see there is a triangle, so CA raises to 1. So based on this, can we also estimate what is the average clustering coefficient for a given random network and the local clustering coefficient of individual nodes in a random network? Now we know that average number of edges expected in a random network is given by P into n minus 1 by 2 based on our assumption of binomial distribution. So we can say that extending the same analogy to I neighbors, expected number of edges between I neighbors would be equal to Ni, or Ni neighbors would be P into Ni into n minus 1 divided by 2. And we know that total maximum edges that can be present are equal to Ni into Ni minus 1 divided by 2. Hence the local clustering coefficient can be derived as 2 upon Li into Ni into Ni minus 1 by divided by 2. In fact, we have 1 2 here, this 2 goes here, and we have 1 1 2 here, so these cancel out, and this is and if we replace this Li by P times this, we end up with Ci equal to P, and we know that for random graphs P can be written as average K upon N. So what it means, that in case of random networks, clustering coefficient is only function of average degrees upon number of nodes. Now this equation has two inferences. One is that Ci is independent of node degree, and as number of nodes in network increase, since Ci is decreasing, average clustering coefficient of network should also decrease. So if you look at these green lines, this is what we draw the inferences about some real world networks from the equation that I have just put in box, and these dots represent the behavior of real world systems. For example, in real world systems, you see that as n increases, average C upon average K remains more or less constant. That means there is no relationship between number of nodes in a network and average clustering coefficient in a real world system. Similarly, when we look into the relationship between average K, average clustering coefficient, and individual degrees of node, we see that there exists a negative correlation in real world systems. That is, as the higher degree nodes, they tend to exhibit less clustering coefficient. However, random network theory predicts that it should be a straight line, because this relation says that Ci only depends on average degree and number of nodes that are present in the network. Now this means that most of the real world systems that we observe, like scientific collaboration, internet, protein interactions, they may not follow the theory of Ardoshreni networks. So next question arises, where do these real world systems fall? And if real world systems are not ER networks, why we should even bother studying ER networks? And I will try to address these two questions in our next lecture. Thank you.